Look at a piano keyboard. There are white keys, there are black keys, and if we count all the notes from C to the next C, we get 12. But why 12? Why not 10? Why not 20? Why not 100? To understand this, we need to stop thinking about sound as names like C or G. Instead, we need to think about sound as numbers. A musical note is a vibration. For example, if one note vibrates at a certain frequency and another note vibrates exactly twice as fast, we hear something special. These notes sound different, but somehow they also feel like the same note. This interval is called an octave, so the frequency ratio of an octave is 1 to 2. Now let's try another important ratio. If we multiply the frequency by 3 halves, we get a note that sounds extremely stable with the original note. This interval is called a perfect fifth, so now we have two important numbers. Octave equals 2, perfect fifth equals 3 halves. Now here's the experiment. Start with C, then multiply its frequency by 3 halves. This gives us G. Now do it again. But 9 over 4 is greater than 2. That means this note has moved beyond our original octave, so we divide it by 2 to bring it back down. This note is D. We can repeat this process. Multiply by 3 halves, and whenever the result moves outside the octave, divide it by 2. By moving upward and downward through perfect fifths, we can construct the notes surrounding C. When we move all of them into the same octave and sort them from low to high, we get C, D, E, F, G, A, B, C. This is a C major scale created using Pythagorean tuning. These notes are built from simple frequency ratios, which is why many intervals in Pythagorean tuning sound so pure. Now let's keep moving upward by perfect fifths. After 12 fifths, we expect to return to C. On a modern piano, E sharp and F use the same key, so it may look as though the circle has closed, but mathematically, the final note is slightly different from C. The chain of perfect fifths almost closes, but not perfectly. To understand why, let's compare 12 fifths with 7 octaves. If we stack 12 perfect fifths, the ratio is 3 halves to the power of 12, but traveling upward by 7 octaves gives 2 to the power of 7. If the system closed perfectly, these two numbers would be equal. But when we calculate them, they are close, very close, but they are not equal. The ratio between them is approximately 1.01364. This small difference is called the Pythagorean comma. The word comma makes it sound insignificant, but this tiny mathematical gap creates a serious musical problem. If every fifth keeps the pure ratio 3 halves, the 12-note cycle cannot close perfectly. The remaining gap has to appear somewhere, creating one badly out-of-tune interval known as the wolf fifth. So musicians faced a choice: keep some intervals perfectly pure and let others sound wrong, or make every interval slightly imperfect so that every key can be used. Modern pianos choose the second solution. This is called 12-tone equal temperament. In equal temperament, the octave is divided into 12 exactly equal steps. The total ratio must still be 2 because the final note is 1 octave higher. So the ratio of each step is 2 to the power of 1/12. The difference may sound subtle. That is partly because we are hearing the notes as a melody, one at a time. The differences become easier to notice when notes are played together as intervals or chords. But the two recordings are mathematically different. The Pythagorean version is built from pure perfect fifths. The equal-tempered version is built from 12 equal divisions of the octave. Equal temperament does not make every interval perfectly pure. Instead, it spreads the Pythagorean comma across the tuning system. Every fifth becomes slightly imperfect, but no single fifth is destroyed. The circle can finally close. The same 12 keys can be used in C major, F sharp major, B flat minor, or any other key. So why are there 12 notes? 12 perfect fifths come remarkably close to 7 octaves. Close enough to create a practical musical system, but not close enough to be mathematically perfect. The 12 notes of the piano are the result of a compromise between two powerful ratios. Octave equals 1 to 2, perfect fifth equals 2 to 3. The answer is the first scale was equal temperament and the second was Pythagorean tuning. They may have sounded almost identical, but the frequencies of several notes were slightly different. Thank you for watching. Bye.